Look up tonight. Find a star, any star. It does not matter which one. Just pick a point of light somewhere in the darkness above you and hold it in your mind for a moment. That star is burning. Right now, as you look at it, hydrogen atoms are colliding in its core with such force that they fuse together, releasing energy in the form of light and heat. The temperature at the core of a typical star is somewhere around 27 million degrees Fahrenheit. At that temperature, atoms do not behave like they do at the temperatures we experience on Earth. They are stripped of their electrons. They are moving so fast that when two hydrogen nuclei collide, they can overcome the electromagnetic repulsion that normally keeps positively charged particles apart, and they fuse into a new element, helium. The process releases an enormous amount of energy, and that energy is what makes the star shine. The energy produced in the core does not immediately escape into space. It takes a very long time to work its way outward through the star, bouncing between particles, being absorbed and re-emitted, making a slow, random walk from the core to the surface. In the case of the Sun, the average photon of light takes somewhere between 10,000 and 100,000 years to travel from the core to the surface. When it finally emerges and escapes into space, it travels at the speed of light, crossing the 93 million miles between the Sun and Earth in about 8 minutes. The light hitting your eyes when you look at the Sun left the surface 8 minutes ago, but it was born in the core tens of thousands of years before that. Now, think about the stars you can see at night. The nearest one, Proxima Centauri, is about 4 light years away. The light you see from it tonight left that star 4 years ago. Other stars in the night sky are hundreds or thousands of light years away. The light from the Andromeda Galaxy, visible as a faint smudge to the naked eye on a clear, dark night, left that galaxy about 2.5 million years ago. When you look at the night sky, you are not seeing the universe as it is now. You are seeing it as it was, across a range of different times in the past. Each point of light, a message that has been traveling toward you for years or centuries or millennia, all of which is to say that stars feel permanent. They feel like fixtures. They feel like the night sky is simply the way the universe looks, the default state of things, the backdrop against which all of life plays out. We named the stars. We navigated by them. We built mythologies around them. We organized our calendars by their movements. For as long as human beings have been conscious enough to look up, the stars have been there, and the assumption buried deep in our intuition, so deep that we rarely examine it, is that they will always be there. But they will not. Not even close to always. Every star you have ever seen is dying. Slowly, yes. Over timescales so vast that the word slow stops being adequate. Over timescales that make the entire span of human civilization look like a single frame in a very long film, but dying nonetheless. Every star in the universe is engaged in an irreversible transaction. It takes hydrogen, the simplest and most abundant element in the universe, and converts it into helium and energy. The energy escapes into space, the helium accumulates, and the supply of hydrogen, while enormous, is not infinite. This is true for every star without exception. The brilliant blue-white supergiants that burn hundreds of thousands of times more brightly than the Sun, so luminous that they can be seen from other galaxies with the naked eye, burn through their hydrogen so recklessly fast that they last only a few million years before running out. The medium stars like the Sun, more careful and more patient, burn for billions of years. The small, dim red dwarfs, the most common stars in the universe, burn so slowly and so efficiently that they can last for trillions of years. But all of them, in the end, reach the same conclusion. The hydrogen runs out. The fusion stops. The light goes out. When the last star in the universe burns through its last hydrogen, something will happen that has never happened before in the history of the cosmos. The lights will go out, every single one of them, everywhere, all at once, in the grand scheme of things, in the same way that everything that has ever happened in the observable universe has happened within a tiny fraction of the full timeline of cosmic history. The universe will go dark in a way it has not been dark since before the very first star ignited billions of years ago. But here is what makes this story truly extraordinary. That moment, the death of the last star, is not the end. Not even remotely the end. What comes after the last star dies is a journey through timescales so enormous, so difficult to grasp, so far beyond anything that human language was built to handle, that the entire history of the universe from the Big Bang to today looks like a single heartbeat compared to what follows. The death of the stars is not a conclusion. It is barely an introduction. It is the end of the opening act of a story, whose remaining acts will take longer to play out than the current age of the universe multiplied by numbers that have no everyday meaning. Tonight, we are going to travel to the end of everything, through the slow dimming of the stars over 100 trillion years, through the death of the last red dwarf, the final light in a darkening universe, through the long, cold era of stellar corpses drifting in the dark, through the dissolution of matter itself, through the evaporation of black holes over timescales that make the current age of the universe look like less than a rounding error, all the way to a universe so cold, so empty, so utterly exhausted, that time itself becomes a concept without content, a clock that still ticks but measures nothing. It will take a while. The universe is not in a hurry. Neither are we. Before we can talk about the end of the stars, we need to understand the framework that cosmologists use to describe the long-term future of the universe. Because the universe, strange as this sounds, has ages. Not ages in the way that human history has ages, with clear, documented turning points and scholars arguing about dates, but ages in a deeper structural sense, defined by what kinds of objects dominate the universe and what kinds of physical processes are most important. The system most widely used to describe these cosmic ages comes from a remarkable book called The 5 Ages of the Universe, written by physicists Fred Adams and Gregory Laughlin and published in 1999. Adams and Laughlin divided the future of the universe into 5 distinct eras, each characterized by the dominant structures and processes of that period, and each separated from the next by transitions that are gradual rather than abrupt. It is a framework that has held up remarkably well in the decades since it was published, and it provides the backbone for everything we will discuss tonight. The era we currently live in is called the Stelliferous era. The name comes from the Latin word stellifer, meaning star-bearing. It is, simply put, the age of stars. The era when the universe is full of burning stars producing light and heat and the complex chemistry that makes planets and life and civilization possible. The Stelliferous era began roughly 200 million years after the Big Bang, when the universe had cooled enough and the density of matter had concentrated enough in certain regions that the first clouds of hydrogen and helium collapsed under gravity and ignited nuclear fusion. This moment, sometimes called cosmic dawn, was the universe turning on its lights for the first time. Before it, the universe was dark, filled with gas, but producing no light of its own. After it, the universe blazed with the fires of the first stars. Those first stars were very different from the stars we see today. They were enormous, enormously massive, hundreds or even thousands of times the mass of the sun. They burned with extraordinary brightness and died quickly and violently after only a few million years. But in dying, they scattered into the universe the first generation of heavy elements, elements heavier than hydrogen and helium that had been forged in their cores. Carbon, oxygen, nitrogen, silicon, iron, the raw materials for planets, the raw materials for life. These first stars, sometimes called population 3 stars, seeded the universe with the chemistry of complexity. Subsequent generations of stars formed from gas enriched by those first stellar deaths. Each generation produced and scattered more heavy elements. Over billions of years, the chemical composition of the universe gradually changed, growing richer in the elements that allow planets like Earth to form and that allow the chemistry of biology to operate. And through all of this, the Stelliferous era has continued. For 13.8 billion years now, stars have been forming, burning and dying, and new stars have been forming from the remains. The universe today contains something on the order of 2 trillion galaxies, each containing hundreds of billions of stars on average. The total number of stars in the observable universe is estimated at somewhere around 1, followed by 24 zeros. Every single one of them is burning hydrogen into helium at this very moment, and the Stelliferous era will continue for a very long time yet, not forever, but for an almost unimaginably long time. Current cosmological models suggest that the last stars will die somewhere around 100 trillion years from now. 100 trillion years. The universe is currently 13.8 billion years old. 100 trillion is more than 7,000 times that. If the entire Stelliferous era were mapped onto a single day, the current moment would correspond to roughly the first 12 seconds after midnight. We are barely into the opening moments of the age of stars. The vast majority of it lies ahead. To put it another way, imagine that each year in the history of the universe so far corresponds to a single step. You have taken 13.8 billion steps. But to reach the end of the Stelliferous era from the beginning, you would need to take 100 trillion steps. The steps you have taken so far represent less than 1/10 of 1% of the total journey. We are extraordinarily early, but the Stelliferous era is not indefinite. The clock is running, and the mechanism driving it toward an end is simple: hydrogen. Stars form from hydrogen. Stars burn hydrogen. Hydrogen, once burned into helium inside a star, does not come back. The universe has a finite supply of hydrogen available for star formation, and with each passing generation of stars, that supply diminishes. Over the coming hundreds of billions and trillions of years, star formation will slow and eventually stop. When it stops, the Stelliferous era ends, and everything changes. Before we follow the universe into darkness, we need to understand how stars die. Because the way a star dies determines what it leaves behind, and what it leaves behind is what populates the universe during the long cold eras that follow the Stelliferous era. The deathbed of a star is the birth certificate of the future universe. Stars die in different ways, depending on their mass. This single fact, the relationship between a star's mass and its eventual fate, is one of the most important insights in all of astrophysics. And the range of fates is extraordinary, from quiet and gradual to sudden and catastrophic. Let us start with the stars most similar to our own Sun. Stars in the medium mass range, from about half the mass of the Sun to about 8 times the mass of the Sun, follow a broadly similar trajectory. For most of their lives, they burn hydrogen in their cores steadily and consistently, converting hydrogen to helium and producing energy that keeps them stable against gravitational collapse. This phase, called the main sequence, lasts for millions to billions of years, depending on the star's mass. More massive stars in this range burn their hydrogen faster and die sooner. Less massive ones burn slowly and live longer. When the hydrogen in the core runs out, the star faces a crisis. Without the energy of fusion to push outward against gravity, the core contracts. This contraction heats the surrounding shell of hydrogen that has not yet been burned, causing fusion to ignite in that shell. The energy from the shell fusion puffs out the outer layers of the star dramatically. The star swells into what is called a red giant, expanding to many times its original radius. In the case of our Sun, this expansion will be so dramatic that the Sun will swallow the orbits of Mercury and Venus, and possibly Earth as well, depending on how much mass is shed during the process. In the core of the red giant, temperatures eventually get high enough for helium fusion to begin. Helium nuclei fuse into carbon and oxygen. But helium fusion is less efficient than hydrogen fusion, and it lasts for a much shorter time. When the helium runs out, the core contracts again. For stars in the mass range we are discussing, the core cannot get hot enough to fuse carbon. The process stops here. What happens next is beautiful and strange. The outer layers of the star are expelled into space, forming a glowing shell of gas called a planetary nebula. The name is misleading, a historical accident from a time when early astronomers thought these fuzzy circular objects looked like planets through small telescopes. They have nothing to do with planets. They are the expelled outer layers of a dying star, illuminated by radiation from the hot remnant at the center. And what is that remnant? It is the core of the dead star, a dense, hot sphere of carbon and oxygen, roughly the mass of the Sun compressed into a volume about the size of Earth. This object is a white dwarf. It is supported against further gravitational collapse, not by fusion reactions, which have stopped entirely, but by a quantum mechanical effect called electron degeneracy pressure. This is a consequence of the Pauli exclusion principle, which prevents two electrons from occupying the same quantum state. As the white dwarf is compressed, eventually there is literally no room for any more compression without violating this principle, and the pressure this creates holds the white dwarf up indefinitely. The white dwarf is extremely hot when it first forms. It glows white and then yellow and then orange as it slowly cools over billions of years, but it has no internal energy source. It is simply radiating away the heat it accumulated during its life as a star. Over vast timescales, it will cool and fade and eventually become dark and cold. This cold, dark remnant is called a black dwarf. No black dwarfs yet exist in the universe because none of the white dwarfs that have formed so far have had time to cool that completely. The universe is not yet old enough to have produced even one. Now let us look at more massive stars. Stars that begin with more than about 8 times the mass of the Sun follow a completely different and far more violent trajectory. These stars are prodigious energy producers, burning through their hydrogen much faster than smaller stars. A star 20 times the mass of the Sun lives for only about 10 million years before exhausting its core hydrogen, compared to the 10 billion year lifespan of a star like the Sun. When a massive star exhausts its hydrogen, it can fuse helium. When it exhausts its helium, it can fuse carbon. When it exhausts its carbon, it can fuse neon, then oxygen, then silicon. Each stage of fusion produces a new element and releases energy, but each stage is less efficient and lasts for a shorter time than the previous one. The silicon fusion stage, which produces iron, lasts only for days. Iron is the end of the road. Iron is the most stable nucleus in nature. Fusing iron does not release energy, it consumes it. When a massive star builds up an iron core, fusion stops in the core, and the star faces a catastrophic structural crisis. The iron core, which has been building up and compressing under gravity, suddenly collapses in a fraction of a second. The collapse is so rapid and so violent that the core, which was roughly the size of Earth, shrinks to a sphere about 12 miles across in less than a second. This collapse releases an enormous amount of energy, more energy in a fraction of a second than the Sun will produce in its entire 10 billion year lifetime. A significant fraction of this energy blasts the outer layers of the star outward in a supernova explosion. The explosion is so bright that it can outshine the entire galaxy, containing billions of stars, for weeks or months. The outer layers of the star, enriched with heavy elements forged during the star's life and during the explosion itself, are scattered into the interstellar medium, where they will eventually become part of new stars and planets. What is left at the center depends on the mass of the star. For stars up to about 20 or 25 solar masses, the collapse of the core produces a neutron star. A neutron star is even more extreme than a white dwarf. At the densities reached during the core collapse, electrons and protons are forced to combine, forming neutrons. The entire object becomes a star made almost entirely of neutrons, with a diameter of about 12 miles and a mass between 1 and 2 times that of the Sun. A teaspoon of neutron star material would weigh about 1 billion tons. The density is so extreme that atomic nuclei are essentially touching each other. For the most massive stars, even the neutron degeneracy pressure is not enough to halt the collapse. The core continues to collapse past the neutron star stage and forms a black hole, a region of space where the gravitational field is so intense that the escape velocity exceeds the speed of light. Not even light can escape from a black hole. Whatever goes in does not come out. And then there are the red dwarfs. These small, dim, cool stars, which make up the vast majority of all stars in the universe, are so efficient at burning their hydrogen that they die in a very different and much quieter way. Red dwarfs are fully convective, meaning their interior is constantly mixed by convection currents, like a pot of water being stirred. This means they can access their entire hydrogen supply for fusion, not just the hydrogen in the core. They burn through their hydrogen remarkably thoroughly before they go out. Current models suggest that red dwarfs below about a certain mass threshold simply cool and fade gradually when their hydrogen is exhausted, without going through a dramatic red giant phase. They become slowly cooling helium-white dwarfs and eventually, over trillions of years, black dwarfs. All of these remnants, the white dwarfs, the black dwarfs, the neutron stars, the black holes, are what the universe is left with after the Stelliferous era ends. They are the building materials of the long, dark eras that follow. Before we leave the Stelliferous era, we need to spend more time with the red dwarfs, because these unassuming, dim, easily overlooked stars are the final act of the stellar era. They are the last light, and the story of the last 100 trillion years of star burning is essentially the story of these small, patient fires burning on long after everything more spectacular has gone out. Red dwarfs are defined as stars with masses between about 8% and 50% of the mass of the Sun. They are the most common stars in the universe by a substantial margin. In the Milky Way, more than 70% of all stars are red dwarfs. If you randomly picked a star from our galaxy, chances are better than 2 to 1 that you would pick a red dwarf. But you would never know this from looking at the night sky. Not a single red dwarf is visible to the naked eye, despite the fact that the nearest star to our solar system is 1. Proxima Centauri, a red dwarf just 4.2 light-years away, cannot be seen without a telescope. They are simply too faint. The most luminous red dwarfs are still only about 10% as luminous as the Sun. The least luminous are only about 1/10,000th as bright. What red dwarfs lack in brightness, they more than compensate for in longevity. Because they burn at lower temperatures and with less intensity, they consume their hydrogen far more slowly than Sun-like stars. And because they are fully convective, as we discussed, they can use essentially all of their hydrogen, not just what happens to be in the core. The combination of lower burning rate and higher fuel efficiency gives red dwarfs stellar lifetimes that make the Sun's 10 billion-year lifespan seem brief. A red dwarf with half the mass of the Sun will burn for roughly 60 to 80 billion years, nearly 10 times the current age of the universe. A red dwarf with 20% the mass of the Sun will burn for around 2 trillion years, more than 100 times the current age of the universe. And a red dwarf with just 10% the mass of the Sun, barely large enough to sustain nuclear fusion at all, may burn for 10 trillion years or more, 700 times the current age of the universe. These are the last fires, when the Sun-like stars have been white dwarfs for billions of years, when the massive blue giants have been neutron stars, and black holes for billions of years more, when the history of human civilization is so ancient that no record of it survives anywhere in the universe, the red dwarfs will still be burning, dim and red and patient, scattered across what were once galaxies, burning through their hydrogen at a pace that makes every other star look reckless. But even they will end. One by one, over tens of trillions of years, the red dwarfs exhaust their fuel. The most massive among them go first, after a few trillion years, leaving helium-white dwarfs behind. The smallest, the dimmest, the most miserly burners of all persist the longest, carrying their hydrogen reserves into the deep future like embers that refuse to go out. But even the most patient fire eventually burns its last. Sometime around 100 trillion years from now, the final red dwarf will reach the end. Not with a supernova, not with any of the drama we associate with stellar death. Just a gradual dimming, a core that can no longer sustain fusion, an object that was once a star becoming an object that is no longer anything but a slowly cooling sphere of helium. The transition is seamless and silent. The universe will not mark the occasion. It will simply continue, as it always does, but darker than before. This is the end of the Stelliferous era. After the last star dies, the universe enters the degenerate era. The name comes from the quantum mechanical property of electron degeneracy that supports white dwarfs and neutron stars against gravitational collapse. It is the era dominated by these stellar corpses, these objects that were once stars and now simply exist, cooling and fading and drifting in the dark. The degenerate era begins at around 100 trillion years after the Big Bang and ends at around 10 to the power of 40 years. The Stelliferous era, all 100 trillion years of it, corresponds to about 10 to the power of 14 years. The degenerate era ends at 10 to the power of 40. The difference in the exponent is 26. That means the degenerate era is 10 to the power of 26 times longer than the entire age of stars. Put a different way, if you took the entire history of stars and used it as a unit of measurement, you would need 10 trillion of those units to measure the degenerate era. The age of stars is not a chapter in the degenerate era. It is a footnote so small it barely registers. The universe during the degenerate era is dark. This is the fundamental fact that shapes everything else about this period. There is no starlight. There are no fusion reactions producing energy anywhere. The sources of heat and light that define the Stelliferous era are gone. What remains are objects that are passively cooling, losing the heat they accumulated during their active lives, radiating it into an increasingly cold and empty space. The dominant objects are white dwarfs, or rather, black dwarfs once they have had time to cool. Remember that a white dwarf has no energy source. It is simply a hot ball of carbon and oxygen held up by electron degeneracy pressure, radiating away its heat into space. The cooling time for a white dwarf to become a true black dwarf, cold enough to be essentially invisible at any wavelength, is longer than the current age of the universe. But the degenerate era is vastly longer than the current age of the universe. Over the course of tens of trillions of years, essentially every white dwarf in the universe will complete its cooling and become a black dwarf, a cold, dark, dense sphere drifting in the dark. The universe will be full of these black dwarfs. Billions upon billions of them, the cooled remnants of billions of years of stellar evolution, each one roughly the mass of the Sun, compressed into a sphere the size of Earth, cold and inert and essentially invisible. They will drift through the dark universe, interacting only gravitationally with each other and with whatever else they encounter. Neutron stars are also present during the degenerate era. They too will cool over these timescales, losing their thermal energy and becoming cold, dark, dense spheres of neutron. Many neutron stars are initially pulsars, rotating rapidly and emitting beams of radio waves as they spin. But as they cool and lose rotational energy, the pulsing stops. Eventually they too become cold and dark. And there are planets. Billions of planets. The remnants of the solar systems that formed during the Stelliferous era, now orphaned from their stars. When a sun-like star swells into a red giant and eventually sheds its outer layers as a planetary nebula, the planets in the outer reaches of the system may survive. When the star becomes a white dwarf, they orbit it at a great distance, slowly cooling as the white dwarf cools. Eventually they too become cold and dark, frozen balls of rock or ice drifting in the dark, still following their orbits around what is now a black dwarf. But while all this cooling is happening, another process is changing the structure of the universe on a larger scale. Galaxies, the great gravitational structures that organize the stars during the Stelliferous era, are slowly dissolving. The dissolution happens through a process called gravitational evaporation. The stars and stellar remnants within a galaxy are not in perfectly stable orbits. They interact gravitationally with every other object in the galaxy, and while most of these interactions are small, they accumulate over time. The net effect over vast timescales is a kind of random walk in orbital energy. Some objects gain energy from these interactions, and others lose it. The ones that gain enough energy eventually have enough to escape the galaxy's gravitational pull entirely. They fly off into intergalactic space, never to return. The ones that lose energy fall into lower orbits, spiraling inward toward the center of the galaxy. This process of gravitational evaporation is slow, extraordinarily slow, but the degenerate era is extraordinarily long. Models suggest that by around 10 to the power of 19 years, many galaxies will have lost a significant fraction of their stars through this process. By 10 to the power of 20 years, the recognizable structure of the Milky Way as we know it today will have largely dissolved. Stars that were ejected from galaxies early in this process will have drifted enormous distances from their original homes, scattered through the vast intergalactic void. The stars that were not ejected spiraled inward toward the galactic center and were consumed by the supermassive black holes that sit there. Every large galaxy has one of these supermassive black holes at its center, and over the course of the degenerate era, these black holes grow by slowly accreting the stellar remnants of the galaxies they inhabit. By the end of the degenerate era, the universe consists of isolated objects drifting through an enormous, dark, expanding void. Black dwarfs and neutron stars and cold planets scattered across distances so vast that the probability of any two of them ever encountering each other is essentially zero. And supermassive black holes sitting alone in the dark in the regions where galaxies used to be, growing slightly larger as they occasionally capture a drifting remnant, but otherwise simply existing. The universe has not ended, but it has become profoundly still. The degenerate era is not completely static. We have described it as dark and quiet, and it is, compared to the Stelliferous era. But over timescales of trillions and quadrillions of years, even very improbable events eventually occur. And some of those events are spectacular, at least by the standards of a universe that has otherwise gone dark. The most dramatic class of rare events during the degenerate era involves collisions between stellar remnants. The universe is full of black dwarfs and neutron stars and white dwarfs drifting through the dark. Most of them will never encounter another object. The distances between them are so vast, and they are moving so slowly relative to each other, that the probability of any two of them colliding is extremely small in any given century. But the degenerate era is not a few centuries long. It is 10 to the power of 40 years long. And over that kind of timescale, even extremely improbable events become inevitable. When two white dwarfs or black dwarfs collide, the result depends on their combined mass. If the combined mass exceeds a critical threshold known as the Chandrasekhar limit, about 1 4/10 times the mass of the Sun, the combined object cannot be supported by electron degeneracy pressure. It collapses, and the collapse triggers a thermonuclear explosion, a supernova, a type Ia supernova, to be precise, the same kind of supernova that astronomers use as standard candles to measure distances across the universe today. This is an extraordinary thought. Long after the last star has burned out, long after the universe has gone dark and cold, supernovae will still occasionally occur. Not from living stars dying, as in the Stelliferous era, but from dead stars colliding. The universe, in the degenerate era, will still occasionally produce brilliant flashes of light brighter than entire galaxies, in regions of space where no living star has burned for trillions of years. These collision supernovae will be extraordinarily rare. The probability of any two specific black dwarfs colliding in any given century is negligibly small. But there are an enormous number of black dwarfs, and the degenerate era is an enormous length of time. Models suggest that these events will occur, scattered through the vast dark timeline of the degenerate era, each one a brief, brilliant flash of light in a universe that otherwise produces no light at all. Similarly, neutron star collisions will occasionally occur. Two neutron stars that are orbiting each other in a binary system, gradually spiraling together as they lose energy by emitting gravitational waves, will eventually merge. This merger produces what is called a kilonova, an explosion that releases an enormous amount of energy and produces some of the heaviest elements in the periodic table, including gold, platinum, and uranium. During the Stelliferous era, kilonovae are thought to be the primary source of these elements in the universe. During the degenerate era, they will still occasionally occur, adding more of these elements to an interstellar medium that has almost no gas left in it. Brown dwarfs, objects that formed like stars but never had enough mass to ignite sustained hydrogen fusion, are another population that persists into the degenerate era. Over extremely long timescales, brown dwarfs occasionally collide with each other. If two brown dwarfs collide and their combined mass is large enough, the resulting object can be massive enough to ignite hydrogen fusion. A new star is born, briefly, in a universe where no new stars should exist. These collision stars, sometimes called blue straggler stars, by analogy with a class of objects seen in globular clusters today, burn their new hydrogen supply and die relatively quickly, but they are a reminder that the degenerate era is not completely static. These rare events do not change the overall arc of the degenerate era. They do not prevent the cooling of the black dwarfs or the dissolution of the galaxies or the eventual dominance of the black holes. They are footnotes in an otherwise quiet story. But they are real. They will happen. And each one, a brief, brilliant flash in a universe that has otherwise gone dark, is in its own way a remarkable thing. The universe in the degenerate era is not completely dead. It is just very, very quiet, with occasional explosions to remind you that physics never fully stops doing things. Now we arrive at one of the great open questions in physics. A question that our most sophisticated experiments have not yet definitively answered. A question whose answer determines what happens during and after the degenerate era. Do protons decay? A proton is not just a particle. It is the foundation of all ordinary matter. Every atom in the universe has a nucleus containing at least one proton. The hydrogen atom, the simplest element, has one proton in its nucleus. Carbon has 6. Iron has 26. The number of protons in a nucleus determines what element it is. Everything you have ever touched, seen, eaten, breathed, or thought about is made of atoms, and every one of those atoms has protons in its nucleus. We have never, in all the history of physics, observed a proton spontaneously decaying. When physicists say a particle decays, they mean it spontaneously transforms into lighter particles, releasing energy in the process. Protons appear to be completely stable. They do not decay. They just sit there, protons, forever, apparently immune to any process that would cause them to change. But some theoretical frameworks in physics predict that protons are not truly stable. Grand unified theories are attempts to merge the strong nuclear force, the weak nuclear force, and the electromagnetic force into a single unified description. Many versions of these theories predict that protons can decay, with the proton transforming into a positron and a neutral pion, which then itself decays into 2 photons. The half-life predicted by these theories varies widely, but the most optimistic predictions place it at around 10 to the power of 34 years. More conservative versions of these theories predict half-lives of 10 to the power of 40 years or longer. These numbers are so astronomically large that it is essentially impossible to observe proton decay by watching a single proton. But physicists have found a clever way to look for it anyway. If you have enough protons in one place, even a very long half-life means that some of them should be decaying right now. The most famous experiment designed to detect proton decay is the Supernovae detector in Japan, a tank containing 50,000 tons of ultra-pure water watched by thousands of sensitive photodetectors. Water molecules contain protons, so the tank contains an enormous number of them, around 10 to the power of 33. If protons decay with a half-life of 10 to the power of 34 years, then roughly 10 protons in that tank should be decaying every year, producing a detectable flash of light. Supernovae has been running for decades. In all that time, it has detected 0 confirmed proton decay events. This tells us that if protons decay, their half-life is longer than about 10 to the power of 34 or 35 years. Either protons are stable, or they decay on a timescale longer than our best experiments can probe. This uncertainty matters enormously for the far future of the universe. If protons decay, then all of the matter in the universe, all the black dwarfs and neutron stars and cold planets that accumulated during the degenerate era, will eventually dissolve, one proton at a time, randomly. Over staggering timescales, the ordinary matter will convert into lighter particles, positrons, electrons, photons, and neutrinos. By around 10 to the power of 40 years, essentially all of the ordinary matter in the universe will have decayed away if proton decay is real. The black dwarfs, the neutron stars, the cold planets, all of it will be gone, converted into a thin, cold gas of elementary particles. If protons do not decay, the matter persists. The black dwarfs remain cold and inert, but real, for timescales that are effectively infinite by any human measure. The universe during the degenerate era, in this scenario, is full of cold, dark objects that will never dissolve, just drifting apart from each other as the universe expands. Either way, there is one type of object that survives the degenerate era regardless of whether protons decay. One structure that neither cooling nor gravitational evaporation nor proton decay can destroy. Black holes. Black holes are not made of ordinary matter in any meaningful sense. A black hole is a region of space-time where the curvature of space has become so extreme that nothing can escape from it. Whatever fell into the black hole to form it, those particles are gone, converted into the gravitational curvature of the black hole itself. A black hole contains no protons to decay. It is, in a deep sense, made of pure gravity. And pure gravity does not undergo proton decay. As the degenerate era progresses, the black holes remain while everything else fades or dissolves. The universe transitions into the next phase. The black hole era begins somewhere around 10 to the power of 40 years and lasts until roughly 10 to the power of 100 years. 10 to the power of 100. This number has a name. It is called a googol, a word coined specifically to give a name to this particular enormous number. The internet company Google takes its name from a misspelling of this word. A googol years. How long is that? The Stelliferous era, all 100 trillion years of it, is about 10 to the power of 14 years. A googol is 10 to the power of 100 years. The exponent goes from 14 to 100, an increase of 86. Each step up in the exponent is a factor of 10. So a googol is 10 to the power of 86 times longer than the Stelliferous era. That is a factor so large that the entire age of stars, from the first to the last, is so much shorter than the black hole era that it effectively does not register. Imagine the following. Every atom in the observable universe is a star. Every star burns for 10 billion years. And then every star burns for another 10 billion years. And then again, repeat this 100 times. The total time that passes is still vastly shorter than the duration of the black hole era. The numbers are genuinely incomprehensible. We can write them, but we cannot feel them. During the black hole era, black holes are the only significant structures remaining in the universe. Everything else has gone. The ordinary matter has either been consumed by black holes or dissolved through proton decay. What remains is the black holes themselves, sitting in an almost perfectly empty, almost perfectly dark universe. Each black hole exists in almost complete isolation. The expansion of the universe has been accelerating since long before the black hole era began, driven by dark energy. This accelerating expansion has a remarkable consequence. It creates a horizon around each observer, beyond which the universe is receding faster than light can travel. This means that even if you were sitting next to a black hole during the black hole era, the nearest other black hole would almost certainly be beyond your horizon, forever unreachable, with no possibility of any signal ever crossing the gap between you. Each black hole is alone in its own observable universe, surrounded by nothing but the thin, cold photon gas left over from the Hawking radiation of already evaporated black holes and the even thinner gas of cosmic background photons, all redshifted to near zero energy by the expansion of space. The temperature of the universe has dropped to within a fraction of a degree of absolute zero. Nothing is happening. Nothing can happen. The black holes sit there in the dark, apparently unchanging, apparently eternal. Apparently, because there is a process occurring, even if it is almost imperceptibly slow. Stephen Hawking showed in the early 1970s that black holes are not truly black. They emit a faint, steady trickle of thermal radiation called Hawking radiation, arising from quantum effects near the event horizon. The mechanism that produces Hawking radiation is rooted in one of the strangest aspects of quantum mechanics, the nature of the vacuum. In quantum field theory, what we call empty space is not truly empty. It seethes with what are called virtual particles. The uncertainty principle of quantum mechanics allows brief violations of energy conservation, and the vacuum takes advantage of this by spontaneously producing pairs of particles and antiparticles that appear and then annihilate almost immediately, too short-lived to be directly observed. At the event horizon of a black hole, something unusual can happen to these virtual pairs. One particle of a pair can fall across the event horizon before the two particles can annihilate. Once inside the event horizon, that particle can never escape. It is gone. The other particle, left without a partner to annihilate with, escapes to infinity as a real particle. It carries away real energy. Where does that energy come from? It comes from the black hole itself. The black hole's mass decreases slightly each time a Hawking particle escapes. The rate of mass loss is extraordinarily slow for massive black holes because the Hawking temperature, the temperature of the radiation emitted, is inversely proportional to the mass. The more massive the black hole, the colder its Hawking radiation and the slower its mass loss. A stellar mass black hole, with a few times the mass of the Sun, emits Hawking radiation at a temperature of about 100 billionths of a degree above absolute zero. For comparison, the current cosmic microwave background temperature is about 2.7 degrees above absolute zero. The black hole is currently absorbing radiation from the universe faster than it emits Hawking radiation. It is actually gaining mass rather than losing it. But the universe is cooling. The cosmic microwave background temperature drops as the universe expands. Eventually, as the universe gets cold enough, even the most massive black holes will be warmer than their surroundings, and they will begin to lose mass. And then the countdown truly begins. For a stellar mass black hole, the total evaporation time through Hawking radiation is roughly 10 to the power of 67 years. For a black hole with 1 million solar masses, it is roughly 10 to the power of 83 years. For a supermassive black hole with 1 billion solar masses, somewhere around 10 to the power of 90 years. And for the very largest black holes we know of, those containing tens or hundreds of billions of solar masses, the evaporation time approaches 10 to the power of 100 years, the googol mark. For most of this time, essentially, nothing happens from a macroscopic perspective. The black hole sits there. It loses mass at an infinitesimally slow rate. Nothing changes perceptibly over any time scale that would be meaningful. But the Hawking radiation is there, carrying away mass, not stopping, not slowing, as inexorable as erosion on a rock. And very gradually, Over the course of the black hole era, the black holes shrink. As a black hole shrinks, it gets hotter. As it gets hotter, it radiates faster. As it radiates faster, it shrinks more quickly. This feedback loop is initially negligible, but it accelerates. In the final stages of a black hole's life, the process becomes explosive. The last tiny remnant of the black hole, shrunken now to subatomic scales, evaporates in a brief burst of very high energy radiation. After lasting for perhaps a googol years in near-perfect isolation, the black hole dies in a fraction of a second, and then it is gone. Let us take a moment to appreciate what this means in human terms, even though human terms are almost completely inadequate here. You are made of atoms. Those atoms contain protons and neutrons and electrons. The electrons are elementary particles that, as far as we know, have no internal structure. But the protons and neutrons are made of quarks, and quarks, together with electrons and a handful of other particles, are the building blocks of all ordinary matter. When a black hole evaporates through Hawking radiation, it converts all of its mass back into these elementary particles and photons. The mass that went in, whether it was hydrogen gas or a dying star or a planet or anything else that fell across the event horizon, comes back out as a thermal bath of radiation. The specific information about what fell in is, controversially, scrambled or lost. This is the black hole information paradox, one of the deepest unsolved problems in theoretical physics. Stephen Hawking initially argued that the information was genuinely destroyed, which would violate a fundamental principle of quantum mechanics. Later in his life, he changed his position. The debate continues among physicists today. But whatever the ultimate answer, the mass comes back out as radiation, and then it disperses into the expanding universe, and then the black hole is gone. The universe, after the last black hole evaporates, contains no black holes. For the first time since the first black holes formed from the first supernovae, the universe has none of them. This is a profound change in the nature of the universe, even though by this point, nothing is around to notice it. The universe has lost its last gravitational anchors, its last massive structures, its last concentrations of anything. What remains is spread as uniformly as physics allows, and then it is gone. After the last black hole evaporates, the universe enters the dark era. There is no sharp boundary, no event that marks the transition. The last black hole disappears, and the universe simply continues, because the universe always continues. What remains is almost nothing. Photons carrying almost no energy, their wavelengths stretched by the expansion of space to lengths of light years or more. Neutrinos streaming through an essentially empty universe, interacting with almost nothing, just drifting. Electrons and positrons spread so thin that the average distance between an electron and the nearest positron is incomprehensible. Possibly some dark matter particles, whatever they turn out to be, also drifting through the void. The temperature of the universe is so close to absolute zero that the difference is negligible for any practical purpose. The universe is cold in a way that goes beyond ordinary language. It is cold in the sense that essentially all thermal energy has been dissipated, spread uniformly throughout an ever larger volume of space, diluted to near nothingness. Even in this state, one last physical process continues. Electrons and positrons, despite being spread across unimaginable distances, will occasionally find each other. Not often. Not in any way that would seem frequent, even on the timescales we have been discussing. But occasionally, by pure chance, an electron and a positron will drift close enough to each other that they can interact. If they are moving slowly enough relative to each other, they will not immediately annihilate. Instead, They will enter a bound state, with the electron and positron orbiting each other, held together by the attraction between their opposite charges. This bound state is called positronium. It is, in a sense, an atom. Not a normal atom, because normal atoms have a nucleus made of protons and neutrons at the center. Positronium has a positron at the center, orbited by an electron, and both of them are matter and antimatter, respectively. It is the simplest possible atom built from matter and antimatter. Positronium is unstable. The electron and positron will eventually spiral together and annihilate, converting their combined mass into photons. But in the cold, quiet, dark era, the positronium can exist in states with very long lifetimes before this annihilation occurs. The longest-lived states of positronium can persist for an extraordinary time before the electron and positron finally come close enough to annihilate. Accounting for the rarity of electron-positron encounters and the various possible states of positronium and their lifetimes, the process of clearing the universe of electrons and positrons through positronium formation and annihilation takes around 10 to the power of 141 years. 10 to the power of 141. The googol year black hole era, which we already established as incomprehensibly long, is negligibly short compared to this. The positronium era dwarfs it by the same enormous factor that the black hole era dwarfs the Stelliferous era. After the positronium is gone, there are no more electrons, no more positrons, no more particles with which to build any structure whatsoever. What remains are photons and neutrinos. Photons carrying essentially no energy, with wavelengths so enormous that they are effectively spread across the entire observable universe. Neutrinos, drifting through an empty void at nearly the speed of light, interacting with nothing, going nowhere in particular, experiencing a universe that has nothing to offer them. This is the heat-death state. Maximum entropy, the end of the thermodynamic story of the universe. Entropy, as we discussed earlier, is a measure of disorder, or more precisely, of the number of microscopic arrangements of a system consistent with its macroscopic state. The second law of thermodynamics tells us that entropy always increases in a closed system. The universe is a closed system. And so entropy has been increasing since the Big Bang, through the formation of stars, the death of stars, the evaporation of black holes, the annihilation of positronium. Every physical process in the universe has been, in a thermodynamic sense, increasing the entropy of the universe. Heat death is the state where entropy can increase no further. Not because some rule prevents it, but because there is nothing left from which disorder could increase. Everything is already maximally disordered. All energy gradients have been smoothed out. All temperature differences have been equalized. All concentrations of energy have been dispersed. The universe has settled into the most probable state of all, the state with by far the largest number of microscopic arrangements consistent with it, and it will remain in that state forever. Time still passes in the heat-death universe. The laws of physics do not require events in order for time to proceed. A clock would still tick if there were a clock to tick. A second is still a second, even if nothing happens during it. But nothing does happen. There is no energy available to drive any process. There is no structure to create any complexity. There is no gradient to push anything anywhere. The universe is perfectly uniform, perfectly still, perfectly quiet. It will remain this way for the rest of time. And the rest of time in a heat-death universe is infinite. But infinite time, with nothing happening, raises a question worth examining. What does it even mean for time to pass in a universe where nothing changes? Time, as we experience it, is defined by change. We feel time passing because things happen. Our memories distinguish past from present. Our expectations distinguish present from future. In a universe with no changes, no events, no differences of any kind, the concept of time becomes peculiar. There is nothing to anchor it to. A second is the same as a year, is the same as a googol years, because nothing distinguishes one moment from the next. Some physicists have proposed that in the very long run, even the heat-death state is not completely static. Quantum mechanics allows for fluctuations, even in a system at maximum entropy. Quantum probability does not go to zero. Given truly infinite time, any configuration of particles that is physically possible will eventually occur through random quantum fluctuation, no matter how improbable it is. This includes, in principle, a spontaneous fluctuation that produces a single conscious mind, isolated in the void, experiencing a moment of awareness before dissolving back into the thermal background. These hypothetical minds are called Boltzmann brains, after the physicist Ludwig Boltzmann, who first considered the implications of statistical fluctuations in thermodynamic systems. The Boltzmann brain problem is more than a thought experiment. It is a genuine puzzle in cosmology, because if the universe lasts long enough, and if quantum fluctuations can produce conscious observers, then the overwhelming majority of conscious observers in the history of the universe would be Boltzmann brains, not evolved beings like us. This would imply that our own existence as evolved beings is extraordinarily improbable, which seems to contradict the evidence. Physicists take this problem seriously as a constraint on cosmological models, because any model that predicts a universe old enough for Boltzmann brains to dominate the observer population seems to be in trouble. The time scale for a Boltzmann brain to fluctuate into existence is so long that it makes the positronium era look brief by comparison. But in an eternal universe, it will happen. And it raises the unsettling question of whether the universe, even after heat death, is truly finished, or whether it is simply waiting, in the most extreme possible sense of waiting, for something to happen again. Everything described so far is based on the best current understanding of cosmology and physics. But it is worth spending time with the alternatives, because the universe is under no obligation to behave the way our current theories predict. The most dramatic alternative is the Big Rip. This scenario arises if dark energy, the mysterious force driving the acceleration of the universe's expansion, is not a constant but a form of energy that grows stronger over time. If dark energy increases without limit, then the acceleration of the universe's expansion increases without limit. And if the acceleration increases fast enough, it eventually overcomes every other force in the universe. First, gravity between galaxy clusters is overwhelmed, and the clusters fly apart. Then, gravity within individual galaxies is overwhelmed and galaxies disperse. Then, solar systems fly apart. Then, planets are ripped apart by the expanding space between their atoms. Then, atoms themselves are ripped apart. Then, even atomic nuclei are torn apart. The universe ends not in a quiet fade, but in a violent, total shredding of everything, down to the subatomic level in a finite time. Current observations suggest this is unlikely. The measurements of dark energy we have made are consistent with it being constant, which rules out the most extreme Big Rip scenarios. But the measurements are not precise enough to definitively exclude a dark energy that increases slowly over time, and a slowly increasing dark energy could still lead to a Big Rip on very long timescales. Another alternative, now considered essentially ruled out by observation but worth mentioning for completeness, is the Big Crunch. In the early days of modern cosmology, many physicists believed the universe might eventually stop expanding and begin to contract. If the total density of matter and energy in the universe exceeded a critical threshold, gravity would eventually overcome the expansion and the universe would collapse back on itself in a final, cataclysmic compression. The discovery in the late 1990s that the expansion of the universe is actually accelerating effectively rules out the Big Crunch. A universe that is accelerating its expansion cannot collapse. A stranger possibility is vacuum decay. The laws of physics, as we understand them, involve certain fields that permeate all of space. The Higgs field, for example, is responsible for giving mass to certain particles, and it has a particular value throughout the universe. But quantum field theory raises the unsettling possibility that this value might not be the lowest possible energy state of the field. The universe might be in what is called a false vacuum, a state that is locally stable but not globally stable, like a ball resting in a small dip on the side of a hill rather than at the bottom of the hill. If the universe is in a false vacuum, there is a finite probability at any moment that quantum tunneling could trigger a transition to the true vacuum state. This transition would propagate outward from the point where it began at the speed of light, converting the false vacuum to the true vacuum as it expands. The laws of physics would be different in the bubble of true vacuum, potentially in ways that are completely incompatible with the existence of any structure whatsoever. Anything caught in the expanding bubble would not be destroyed in any conventional sense. It would simply stop existing in the context of the new physics. There would be no warning and no survival. The expanding bubble of true vacuum would arrive at any location at the speed of light, so you could never see it coming. No one knows whether the universe is in a false vacuum. Calculations based on the measured mass of the Higgs boson suggest the universe might be on the edge between a stable and metastable vacuum, a situation that physicists with a sense of humor describe as living dangerously. But the calculations have significant uncertainties. None of these alternative endings are considered likely under current physics. But physics has surprised us before, and it will surprise us again. There is a deeper point here too. Everything we have described about the far future rests on extrapolating physical laws that were derived from observations made within the first 14 billion years of the universe's existence. We are using rules discovered in the opening moments of the cosmic story to predict what happens in its final chapters. The laws have proven remarkably consistent across the conditions we can observe, but the far future involves conditions so extreme, densities so low, timescales so vast, that they lie entirely outside any regime we have tested. It is possible that the laws hold exactly as written all the way to the heat death. It is also possible that they break down or reveal new behavior at some threshold we have not yet reached. The honest answer is that we do not know. The picture we have drawn is our best current understanding, extrapolated as carefully as we can manage. It is not a certainty. It is a prediction. Let us step back from the timescales for a moment and think about what it means to exist right now, in this particular chapter of cosmic history. The universe is 13.8 billion years old. The Stelliferous era will last for 100 trillion years. We are in the opening pages. By the measure of the Stelliferous era alone, we are so early that describing us as early does not capture it. We are not in chapter 1. We are in the preface. And yet here we are, asking questions about the end. The universe did not have to permit this. The laws of physics could have taken values that made galaxies impossible, or stars too short-lived, or chemistry too simple. The cosmological constant could have been larger by a small amount, and matter would never have clumped into galaxies at all. The strength of the strong nuclear force could have been slightly different, and carbon atoms would not be stable. The ratio of the masses of the electron and proton could have been different, and the stable chemical bonds that allow for proteins and DNA and every biological structure would not exist. Any of these changes, modest by the standards of the enormous range of values each constant could in principle take, would produce a universe where nothing like us could ever exist. This is sometimes called the fine-tuning problem, and physicists argue vigorously about what it means and how to explain it. But whatever the explanation, the fact itself is striking. We live in a universe where the constants are tuned, accidentally or otherwise, to values that permit observers to exist. And not just to exist, but to exist at this specific moment in cosmic history, after enough star generations to produce the heavy elements biology requires, before the universe has grown too old and cold for liquid water to pool on planetary surfaces. We did not get here by being central. We are not at the center of the galaxy or the universe. The Sun is an ordinary star. Earth is an ordinary planet. But we arrived at the right time, in a universe with the right constants, and that is a different kind of luck entirely. Not the luck of being special, but the luck of being possible at all. There is a concept in philosophy and cosmology called the anthropic principle, which in its most basic form simply observes that the universe we observe must be compatible with our existence as observers. We could not be here to notice a universe that did not permit us. This is sometimes dismissed as circular, but it carries a genuine insight. Across all the ways the universe could be, we are in one where observers are possible. Whatever you make of that, the universe that surrounds you tonight is the kind of universe that produces minds capable of understanding it. Let us watch the universe age one more time, letting the full sweep of the timeline play out in our minds. Right now, the universe is alive with fire. Billions of galaxies, each containing hundreds of billions of stars, burning hydrogen into helium across a span of space so large that light has been traveling since the Big Bang and has not yet reached the far edge. This is the universe as it exists tonight. As you are watching this, burning, glowing, complex, full of possibility, several billion years from now, the Sun completes the arc we described earlier. Red giant, planetary nebula, white dwarf. The solar system goes quiet. Earth, if anything of it survives the swelling of the Sun, is a cold, bare rock in orbit around a fading white dwarf. The story of our home star is over, but the universe is still full of stars. Other stars are being born and dying, and the sky, as seen from other planets, still blazes with light. The Andromeda Galaxy merges with the Milky Way over the course of hundreds of millions of years, a slow, graceful collision of two spirals that produces a new elliptical galaxy. Individual stars are not destroyed in this collision. The spaces between them are too vast, but the shapes of the galaxies are thoroughly transformed. Trillions of years pass. The massive and medium stars die one by one, leaving their white dwarfs behind. The universe's color shifts as the bright, hot stars go out, and only the cool red dwarfs remain. The sky grows redder and dimmer. Fewer and fewer stars burn. The rate of new star formation has slowed to nearly zero. The universe is using up the last of its hydrogen reserves. Around 100 trillion years, the last red dwarf reaches the end of its reserves. There is no signal, no flash, no final broadcast. The universe simply crosses a threshold it has been approaching for trillions of years, a state in which no nuclear fusion occurs anywhere. For the first time since cosmic dawn, the universe produces no light of its own. The universe is dark, cold, still full of matter in the form of black dwarfs and neutron stars and cold planets and supermassive black holes. but no light of its own. No fusion reactions producing energy anywhere. The degenerate era has begun. Vast stretches of time pass. The black dwarfs cool, the galaxies dissolve, their stars slowly evaporating into intergalactic space or spiraling into the central black holes. The universe expands, carrying the isolated remnants further and further apart. By around 10 to the power of 40 years, ordinary matter is either gone through proton decay or locked up in cold, dark, isolated objects. The black holes remain. The black hole era has arrived. For a googol years, the black holes sit in darkness, slowly, imperceptibly. Hawking radiation carries away their mass. They shrink over astronomical timescales. The universe is darker than at any previous point in its history. Colder, more empty, more perfectly quiet. And then the black holes begin to die. The smaller ones go first, vanishing in brief flashes of radiation. The larger ones persist longer. The very largest hold out until around 10 to the power of 100 years. But they too eventually shrink to nothing. One by one, the last black holes vanish. The universe has no black holes. What remains is photons and neutrinos and the thin plasma of electrons and positrons, all cooling toward absolute zero. The positronium phase plays out over 10 to the power of 141 years, electrons and positrons occasionally finding each other, briefly bonding, annihilating into photons. Eventually, even this stops. Only photons and neutrinos remain. The universe has reached heat death, maximum entropy, the permanent, unchanging silence of a cosmos that has exhausted all of its usable energy and settled into its most probable state. Time continues. But nothing happens. Not tomorrow, not in 1 trillion years, not in a googol years. The universe is done. It is still there. It simply has nothing left to do. Before we travel billions of years into the future, let us make the abstract personal. Let us talk about our sun, our star, the specific burning sphere of hydrogen that makes our existence possible. Because understanding what will happen to the sun gives us a window into what will happen to every other sun-like star in the universe, and it grounds the enormous timescales we are discussing in something we can actually feel connected to. The sun is currently about 4.5 billion years old. It sits comfortably in the middle of its main sequence lifetime, which means it is doing exactly what it has been doing since it formed, fusing hydrogen into helium in its core, maintaining the balance between the outward pressure of that fusion energy and the inward pull of its own gravity, and radiating light and heat into the solar system at a rate that has been remarkably steady for billions of years. The sun is not exactly the same as it was when it formed. It is very gradually getting brighter. As hydrogen in the core is converted to helium, the helium builds up and the core slowly contracts and heats. This makes the fusion reactions slightly more vigorous, and so the sun produces slightly more energy. Over its lifetime, the sun has brightened by about 30% from what it was when it first ignited. In another billion years or so, it will be noticeably brighter than it is today, enough brighter that liquid water will become difficult to sustain on Earth's surface, even with significant changes to the atmosphere. But the main event is still 5 billion years away. That is when the hydrogen in the sun's core finally runs low enough that the core can no longer sustain the outward pressure needed to balance gravity. At that point, the core contracts. The contraction heats the surrounding hydrogen shell, igniting fusion there. The energy from this shell fusion is what causes the outer layers of the sun to swell dramatically. The sun will swell from its current radius of about 432,000 miles. to a radius of somewhere around 150 million miles. That is a factor of roughly 350 times its current size. To put that in perspective, the current distance from the Sun to Earth is about 93 million miles. The Sun's surface will expand to beyond Earth's current orbit. Whether Earth itself survives depends on exactly how much mass the Sun loses during the red giant phase, which affects how the orbits of the planets change, but the prospects for life on Earth at this point are non-existent regardless. The oceans will have been boiled away billions of years earlier by the Sun's gradual brightening. Earth in the red giant era is a barren, scorched rock orbiting inside or just outside a star. The red giant phase will last for about 1 billion years. During this time, the Sun's outer layers are puffed far out into the solar system, and the star appears as a vast, dim red sphere dominating the sky of any surviving outer planet. Jupiter, Saturn, Uranus, and Neptune, orbiting much farther from the Sun, may survive the red giant phase. They will be warmed more than they are today, but they will persist as planets. Eventually, helium fusion begins in the red giant's core. This is a brief and somewhat unstable phase called the helium flash, when helium suddenly ignites in a degenerate core in an explosive burst that lasts only a few seconds but releases an enormous amount of energy. The Sun then settles into a somewhat more compact red giant phase, where it burns helium steadily. But helium fusion is less efficient and lasts for a shorter time than hydrogen fusion. When the helium runs out, the process stops. The outer layers of the Sun are expelled into space, forming a glowing shell of gas that expands outward from the star. This planetary nebula, lit by the ultraviolet radiation from the hot remnant at its center, will be visible from great distances as a beautiful glowing ring or sphere of gas. It will be visible for perhaps 10,000 years before dispersing into the interstellar medium, adding its atoms to the raw material available for future generations of stars, enriching the interstellar medium with carbon and oxygen and other elements forged in the Sun's interior. What remains at the center of the planetary nebula is the core of the former Sun, compressed to roughly the size of Earth, but still containing about half the mass of the original Sun. This is a white dwarf. It is intensely hot when first exposed, glowing blue-white at surface temperatures of over 100,000 degrees. But it has no internal energy source. It is simply hot, and it will cool. Over the next few billion years, the white dwarf cools from blue-white to yellow to orange to red. Its luminosity drops dramatically. The outer planets of the solar system continue to orbit it at great distances, slowly cooling themselves as the white dwarf dims. Eventually, after hundreds of billions of years, the white dwarf dims to a faint red glow. After trillions of years, it becomes a black dwarf, a cold, dark, dense sphere of carbon and oxygen, roughly the size of Earth, drifting in the dark with its frozen retinue of outer planets. This is the fate of our Sun, and it is the fate of every sun-like star in the universe. The universe will be full of them in the degenerate era. 100 billion trillion cold, dark spheres, the cooled hearts of what were once stars, drifting through the expanding void. We have described the physics of each cosmic era, but physics alone does not give a complete picture. Let us try to describe what the universe actually looks like during each of these phases. Right now, during the Stelliferous era, the universe is magnificent. Any direction you look from a vantage point between galaxies, you see galaxies, billions of them, each a glowing structure of light. Some are spirals like the Milky Way, with bright cores and sweeping arms tracing out the locations of the youngest, hottest stars. The overall color of a spiral galaxy is a mixture of the blue-white of young hot stars in the arms and the yellow-orange of older stars near the center. Some galaxies are ellipticals, smoother and more featureless, their blue-white stars long gone and replaced by the older population. Some are irregular, disturbed by recent mergers. Within a galaxy, the sky from a planet, in a system like ours, is full of stars. Thousands visible to the naked eye, hundreds of billions visible to instruments. Light everywhere. Not just visible light, but radio waves, infrared radiation, ultraviolet light, X-rays from hot gas and compact objects, gamma rays from exotic events. The universe during the Stelliferous era is rich and complex across the entire electromagnetic spectrum. As we move into the early degenerate era, this changes completely. The blue-white stars have been gone for billions of years. The last sun-like stars are white dwarfs. The last red dwarfs have only recently gone out. From any vantage point in the universe, there is no starlight. The white dwarfs still glow, faintly, cooling from yellow toward orange toward red. They emit infrared radiation that slowly fades over billions of years. But as they cool, even that fades. The universe grows dark in the infrared. It grows dark in the radio. It grows dark at every wavelength. By the middle of the degenerate era, the universe is visually completely dark. The black dwarfs emit no detectable radiation. The neutron stars are cold. The occasional gravitational interaction between two drifting remnants produces no significant electromagnetic signature. A hypothetical observer with perfect instruments could detect these objects through gravitational effects, through the faint distortion of space-time that any mass produces. But there is nothing to see in the conventional sense. The universe has gone dark. The cosmic microwave background still fills space, but it has been redshifted by the ongoing expansion to wavelengths so long that detecting it requires instruments of extraordinary sensitivity. It is a faint whisper of radio waves, barely distinguishable from nothing. The universe in the degenerate era is radio silent by any standard we would recognize today. As galaxies dissolve, the distribution of objects changes. In the early degenerate era, the black dwarfs and neutron stars are still roughly distributed in the shapes of what were once galaxies, recognizable to a careful observer as regions of slightly higher density. But gravitational evaporation does its work over billions and trillions of years, and those shapes blur and disappear. By the end of the degenerate era, the objects are scattered through an expanding universe, each one isolated by distances so vast that gravitational interaction between them is negligible. The black hole era universe is stranger still. The supermassive black holes sit in a near-perfect void. They are invisible in every conventional sense. They emit no light, no radio waves, nothing detectable at ordinary distances. The only way to know they exist is through the faint distortion of space-time around them, detectable only at very close range, with instruments of extraordinary sensitivity. The Hawking radiation they emit is at temperatures so low, fractions of a degree above absolute zero, that detecting it would require placing a detector within an astronomical unit of the black hole and having it be sensitive to photons of wavelengths measured in light years. Space itself during the black hole era is at a temperature just slightly above absolute zero, set by the background radiation and the faint Hawking radiation from the black holes. The universe is darker, colder, quieter, and more uniform than at any previous point in its history. The black holes are the only structures remaining, and even they are invisible. And then the dark era. After the last black hole evaporates, there are no structures at all. The universe is a thin, perfectly uniform gas of photons and neutrinos spreading through an expanding space. The photons have wavelengths larger than the observable universe. The neutrinos drift at nearly the speed of light through an empty void. The temperature of the universe approaches absolute zero asymptotically, never quite reaching it because there is still some energy present, but coming so close that the difference is immeasurable. This is the final state, not empty in the absolute sense, but empty in every sense that matters. The universe in the dark era is the physical realization of the concept of nothing. Could anything survive the long dark? It is a question that naturally arises when thinking about the far future. Could life, or something like life, survive into the deep future of the universe? Could intelligence or civilization persist into the degenerate era or beyond? This is not purely speculative. Serious physicists, including Freeman Dyson, have thought carefully about the thermodynamics of life in the far future. Dyson's famous analysis from 1979 argued that life could in principle persist forever in a cooling universe by periodically slowing down its metabolism in proportion to the decreasing energy available. The key insight was that what matters is not the rate of thought, but the total number of thoughts. If a mind can slow down its processing to match the declining energy budget, thinking one thought per century instead of one per second, and if it hibernates between those thoughts to conserve energy, then an infinite future could support an infinite total number of thoughts, even with a finite energy supply per unit time. The mind would wake periodically, experience a moment of consciousness, and return to dormancy. Stretched across an infinite timeline, the total experience could be infinite. Dyson's analysis was genuinely hopeful. It suggested that the long dark future of the universe was not necessarily a future without experience or meaning or the continuation of minds. It was a future in which minds would have to adapt radically, becoming slower and more patient. But it was not necessarily a future without minds. However, Dyson's analysis did not account for the cosmological constant, the dark energy that drives the accelerating expansion of the universe. The accelerating expansion creates a horizon around every observer, a boundary beyond which the universe is forever inaccessible because it is receding faster than light can travel. This horizon means that the total amount of energy any civilization can ever access is finite, bounded by what is within their horizon. A finite amount of energy, even used with perfect efficiency, can support only a finite total amount of thought and computation. Dyson's infinite future turns out to be finite after all, bounded by the horizon that dark energy imposes. The cosmological constant appears to place a hard limit on the total amount of information processing that can ever occur in the universe. No matter how clever, no matter how efficient, no civilization can think more thoughts than the finite energy within its horizon allows. The universe imposes an absolute budget, but within the Stelliferous era, the energy budget is enormous. The sun alone has enough remaining fuel to power human civilization at its current energy consumption rate for an almost incomprehensible length of time. And the sun is just one of hundreds of billions of stars in the Milky Way, which is just one of 2 trillion galaxies in the observable universe. The Stelliferous era has 100 trillion years still to run. The energy available within that era, if ever collected and used efficiently, is so much greater than anything human civilization has ever imagined using that the concept of an energy crisis becomes almost meaningless. The conditions for life as we understand it become progressively more difficult as the universe ages. The Stelliferous era is ideal. The early degenerate era, with its cooling white dwarfs, is challenging but not impossible in principle. White dwarfs radiate heat, and that heat could in principle be harvested. The later degenerate era, with its cold black dwarfs and neutron stars, is extremely hostile. The black hole era, powered only by the faint Hawking radiation of evaporating black holes, is almost certainly beyond any conceivable form of life as we understand it. And the dark era is definitively the end of any possibility of biological or computational complexity. We live in the comfortable, early, energy-rich universe. Whatever we or our descendants or whatever comes after us might do with the 100 trillion years remaining in the Stelliferous era is genuinely open. The universe is not running out of time or energy anytime soon by any human standard. The deep future remains, for now, entirely unwritten. There is something genuinely hard about sitting with the heat death of the universe. Not just intellectually hard, the numbers we can write down and accept, but emotionally hard, in a way that deserves honest acknowledgement. The universe will reach a state where nothing interesting can ever happen again. Everything built, everything thought, everything felt, everything loved or feared or wondered about will be physically unreachable. Not just forgotten, not just destroyed, gone in the deepest possible sense. The substrate for any of it to continue will no longer exist. The heat death state is a universe where memories cannot exist because there is nothing capable of holding them, where meaning cannot persist because there is nothing capable of caring about it. It is as complete an ending as physics allows. This naturally feels like a tragedy, and there is a philosophical tradition that says, yes, it is. The impermanence of everything, including the universe itself, is genuinely sad. The appropriate response is a kind of cosmic grief, a recognition that existence is beautiful precisely because it is temporary, and that the ending diminishes it in some way. But there is a competing tradition that pushes back on this. It argues that the heat death does not diminish what happened before it, any more than a person's death diminishes the life they lived. The value of an experience is not determined by how long it lasts. A piece of music is not less beautiful because it ends. A conversation is not less meaningful because it concludes. If the universe produced for a time minds capable of wonder and love and understanding, then that happened. It was real. The heat death that comes after does not reach backward through time and unmake it. The philosopher Albert Camus wrote about what he called the absurd, the collision between the human desire for meaning and the universe's silence on the subject. His answer was not despair but defiance. To imagine Sisyphus happy, to find meaning in the act itself rather than in any outcome. Applied to the cosmic scale, this suggests something similar. The meaning of the Stelliferous era is not in what comes after it. It is in the era itself, in the stars burning and the planets forming and the minds that looked up and asked questions. There is a more practical point too. The heat death is 10 to the power of 100 years away. That number is so enormous that concern about it is not just premature. It is incommensurable with any problem any actual being has ever faced. The Sun will not exhaust its hydrogen for 5 billion years. The Stelliferous era has 100 trillion years remaining. Whatever finitude the heat death represents, it does not press on us. It does not change what is available to any living thing, on any timescale that any living thing could actually experience. What the heat death does do, when we contemplate it honestly, is put everything else in perspective. It reminds us that nothing is permanent. Not civilizations, not species, not planets, not stars, not galaxies, not black holes, not the universe itself. Everything that exists is temporary. And in a universe where everything is temporary, The question of what to do with the time available becomes more urgent, not less. Throughout this video, we have been throwing around numbers so large that ordinary language fails to convey their meaning. Numbers with exponents that climb past anything our intuition can process. And it is worth spending time with this problem. Because if you cannot feel the scale of the timescales involved, the far future of the universe remains abstract in a way that prevents you from really grasping what we are talking about. Let us start with something manageable. 1,000,000. 1,000,000 seconds is about 11.5 days. You can feel that. You have experienced 11 days. 1,000,000 is not an intimidating number. 1,000,000,000 is 1,000 millions. 1,000,000,000 seconds is about 32 years. 1,000,000,000 is already harder to feel. You may have lived 32 years, or you may not have, but you can imagine it. 1,000,000,000 is within the range of human experience, even if it is at the outer edge of it. 1,000,000,000,000 is 1,000 billions. 1,000,000,000,000 seconds is about 32,000 years. That is roughly the entire span of recorded human history several times over. 1,000,000,000,000 is starting to leave the territory of direct human experience. You can construct it intellectually, but you cannot feel it the way you feel 11 days or 32 years. Now consider the timescale of the Stelliferous era. 100 trillion years. That is 100 trillion, which is 100 multiplied by 1 trillion, which is 100 times 32,000 years of seconds, which is 3.2 million years of seconds. We are now so far from any human timescale that the analogy has stopped helping. 100 trillion years is not something a human can feel. It is something a human can only calculate. And yet 100 trillion years is tiny compared to what comes next. The degenerate era lasts until 10 to the power of 40 years. Let us try to get a sense of what that number means. 10 to the power of 40 is a 1, followed by 40 zeros. Written out, it looks like this. 10,000 trillion years. That is 10 to the 14th, which is the Stelliferous era, multiplied by 10 to the 26th. 10 to the 26th is 100 trillion. So the degenerate era is 100 trillion times longer than the Stelliferous era. The Stelliferous era is 100 trillion years. The degenerate era is 100 trillion times 100 trillion years longer. If you spent the entire Stelliferous era trying to count from 1 to the number of years in the degenerate era, saying 1 number per year, you would not get anywhere near done. You would not even be close to done. The ratio is so vast that the Stelliferous era spent counting does not make a measurable dent. And the degenerate era is nothing compared to the black hole era. The black hole era lasts until 10 to the power of 100 years, the googol. The ratio of the black hole era to the degenerate era is 10 to the power of 60. That is a 1 followed by 60 zeros. The degenerate era is to the black hole era what a single second is to about 3 times the current age of the universe, except the ratio is actually much more extreme than that, since we are comparing it to 60 powers of 10 rather than a simple ratio. There is a useful exercise physicists and mathematicians sometimes do when confronting numbers like these. Rather than trying to feel the number directly, you try to feel the number of digits. 10 to the power of 100 has 100 digits. That you can feel. 100 is a comprehensible number. You can picture 100 objects. You can count to 100 in a reasonable time. The googol has 100 digits. The positronium-era timescale has 141 digits. This does not make the numbers feel real in any deep sense, but it gives you a handle on how far they are from everyday experience. Another useful perspective comes from comparing to the number of atoms in the observable universe. The best estimates suggest the observable universe contains somewhere around 10 to the power of 80 atoms. 10 to the power of 80 is a 1 followed by 80 zeros. The googol, 10 to the power of 100, is 10 to the power of 20 times larger than the number of atoms in the observable universe. That means a googol years is so long that if every atom in the observable universe were a year, you would not be a significant fraction of the way through the black hole era. These comparisons do not make the numbers intuitive. Nothing can make numbers this large intuitive, because human intuition simply was not built to handle them. What they do is give you a sense of just how fundamentally different the timescales of the far future are from anything in human experience. The entire history of the universe so far is not just small compared to these timescales. It is negligible. It is less than negligible. It is essentially zero. And yet these timescales are not arbitrary or made up. They follow directly from the laws of physics applied carefully to the objects and processes involved. The evaporation time of a black hole from Hawking radiation is a calculation that flows from the combination of general relativity, quantum mechanics, and thermodynamics. The timescale for positronium formation and annihilation follows from the density of electrons and positrons in the far future universe and the quantum mechanical cross-sections for these processes. The numbers are large because the physics produces large numbers. We did not choose them. The universe did. This is perhaps the most humbling thing about the far future of the universe. The laws of physics, which seem so immediate and concrete when we apply them to things we can touch and see, lead us to conclusions about timescales so vast that the word vast has stopped meaning anything. The laws do not change as we extrapolate further and further forward. They continue to produce answers, specific numbers, specific timescales, specific sequences of events. And those answers, followed faithfully, lead us to a universe that lasts for a googol years after the last star dies, and a universe that keeps going for another 10 to the power of 41 years after that. The mathematics does not blink. The physics does not care that the numbers exceed our intuition. The universe will proceed according to its rules regardless of whether any mind in it can fully grasp the implications. And that, in its way, is one of the most extraordinary things about existence. The universe operates on principles that are, in principle, knowable. We have figured out enough of those principles to trace the timeline from the Big Bang to the heat death. We are small, temporary, improbable creatures who have been here for a cosmic eye blink, and we have managed to work out, at least in outline, the story of everything. The full story from the first moment to the last. That is not nothing. That is possibly the most remarkable achievement in the history of the universe. A reasonable question at this point is, how do we actually know any of this? We cannot travel to the future. We have no direct observations of the degenerate era or the black hole era or the dark era. Everything we have described is, in a sense, a prediction. How confident can we be in it? The answer is that our confidence comes from the consistency and track record of the physical theories on which these predictions rest. Let us walk through the main pillars. The theory of stellar evolution, the science of how stars form, live, and die, is among the most thoroughly tested in all of science. We can observe stars at every stage of their evolutionary cycle. We see young stars just igniting in stellar nurseries like the Orion Nebula. We see stars in their long, stable main sequence phase, billions of them across the sky. We see red giants, bloated and cool, in the late stages of their hydrogen-burning lives. We see white dwarfs, the compact remnants of sun-like stars scattered through the galaxy in enormous numbers. We see neutron stars and black holes, the signatures of massive stellar death. We see planetary nebulae, the expelled outer envelopes of dying stars, glowing in all their colors. We see supernovae, the violent deaths of the most massive stars briefly outshining their entire host galaxies. Every stage predicted by the theory is observed, and the timescales match the predictions with extraordinary precision. When we say the Sun will become a red giant in 5 billion years, we are applying a theory that has been verified against thousands of other stars at every stage of their lives, from the molecular clouds where they form to the cooling white dwarfs they leave behind. The theory of Hawking radiation is less directly verified, because the temperatures involved for astronomical black holes are far too low to detect with current instruments, and we have not yet created or observed an evaporating black hole. But Hawking radiation is derived from the combination of general relativity and quantum field theory, both of which are among the most precisely tested theories in all of science. General relativity has been verified to extraordinary precision through tests of gravitational waves, the bending of light, the precession of Mercury's orbit, the time dilation of clocks in different gravitational fields, and dozens of other measurements. Quantum field theory underlies all of modern particle physics and has been tested to many decimal places. The combination of these two theories in the context of black hole event horizons produces Hawking radiation as a logical consequence. We have strong theoretical reasons to trust it, even without direct observation. The second law of thermodynamics, the law that entropy in a closed system can never decrease, is perhaps the most universally trusted law in all of physics. It has never been observed to be violated in any experiment or observation in the entire history of science. It is not just an empirical generalization. It has a deep statistical explanation rooted in the vast difference in probability between high entropy and low entropy states. The heat death of the universe is simply the long-term application of the second law to the universe as a closed system. If the second law holds, heat death follows. The expansion of the universe, including the acceleration driven by dark energy, is directly observed. The cosmic microwave background, the redshifts of distant galaxies, the distances to type Ia supernovae, the large-scale structure of the universe. All of these measurements are consistent with a universe that is expanding and whose expansion is accelerating. The predictions of the dark energy model for the long-term expansion of the universe are direct extrapolations of what we already observe. None of this means our picture of the far future is certainly correct. There are genuine uncertainties, as we discussed when talking about proton decay and vacuum decay and the nature of dark energy. But the core framework, the death of stars, the cooling of white dwarfs, the evaporation of black holes, the approach to heat death, rests on physics that is among the most well-established in all of science. We have strong reason to trust it. We are not guessing, we are calculating. And the calculations, followed carefully, lead to the cold, dark, silent universe of the deep future. There is one more thing worth saying before we reach the conclusion, and it requires a different kind of stepping back. Not just to the scale of cosmic time, but to the question of what it means that we can trace that scale at all. The laws of physics that govern the universe appear to be mathematical in their nature. They can be written as equations. Those equations have the same form everywhere in the universe and at every point in its history. They do not change. They produce specific, calculable predictions for the behavior of matter and energy under any conditions, including conditions so extreme and so distant in time that no human could ever observe them directly. And yet we can calculate them. We can write down the equation for Hawking radiation and derive that a stellar mass black hole will evaporate in 10 to the power of 67 years. We can apply thermodynamics to the universe as a closed system and predict the heat death. We can extrapolate from observations of stellar evolution today to the lifetime of the last red dwarf 100 trillion years from now. The physicist Eugene Wigner called this the unreasonable effectiveness of mathematics. He was pointing out something genuinely strange. There is no obvious reason why the mathematical structures that human minds find elegant and tractable should turn out to describe the universe with such precision. And yet they do. The equations we write on blackboards, constructed by minds on one small planet around one ordinary star, accurately describe processes occurring in black holes billions of light years away, and events that will occur trillions of years in the future. This is the universe understanding itself through its own products. The matter that came out of the Big Bang eventually organized itself through the long process of stellar evolution and planetary formation and biological evolution into entities capable of writing the equations that describe the Big Bang. The laws that govern the formation of the first stars are the same laws that produced the beings who calculated those stars' lifetimes. There is a loop here that is difficult to fully absorb. The universe, through us, is looking at itself. Whether this loop has any deep significance is a question that physics cannot answer. It is a question for philosophy, or perhaps for whatever comes after philosophy. But it is worth noticing. It is worth sitting with the fact that the universe, in producing minds, produced something capable of comprehending its own beginning and end. The googol story of the cosmos from the Big Bang to the heat death exists in complete form only in the minds of beings who live in the first tiny fraction of it. That knowledge is fragile. It lives in brains that will die. It is recorded in media that will eventually degrade. It will need to be rediscovered by future minds if it is to persist. But right now, it exists. And its existence is a genuine addition to the universe, not just a description of it. Before minds arose, the universe's history simply was. Now, for the first time, there are parts of the universe that know the story. The last star will die. After everything we have explored tonight, this simple fact lands differently than it did at the beginning. 100 trillion years from now, the final nuclear fire in the universe will go out. Not the sun, which dies billions of years before that. Not a brilliant blue giant. Just a small, dim red dwarf somewhere in the dark remnant of what was once a galaxy, spending the last of a hydrogen supply it has been nursing for trillions of years. When it finally runs dry, the Stelliferous era ends. The age of light is over, but the story does not end there. Far from it. The universe will continue for timescales so vast that the entire age of stars, all 100 trillion years of it, will seem like a brief prologue. The black dwarfs will cool. The galaxies will dissolve. The black holes will slowly evaporate over a googol years, each one vanishing in a final flash of Hawking radiation. The electrons and positrons will meet and annihilate over 10 to the power of 141 years. And then there will be only photons and neutrinos cooling toward absolute zero in a universe that has reached maximum entropy and will never change again. It is a vast picture, a humbling picture. The universe is not a permanent thing. It is a story with a beginning and a middle and an end, and the end is as complete as an ending can be. But here is what I want you to hold on to. You are made of atoms that were forged inside stars. The carbon in your cells was produced in the cores of stars that lived and died before the solar system existed. The oxygen in your lungs was scattered into the galaxy by stellar winds and supernova explosions billions of years before Earth formed. The iron in your blood was made in the death throes of massive stars whose remnants are now neutron stars or black holes somewhere in the Milky Way. You are not separate from the story we have been telling tonight. You are made of it. And not just made of it. You understand it. You can trace the chain from the hydrogen plasma of the Big Bang, through the nuclear forges of stellar cores, through the planetary nebulae, and the cooling white dwarfs all the way to the googol year silence of the heat death. You can hold the whole arc in your mind. That is something the universe did not always do. Before minds existed, the arc simply was. Now, for the first time in cosmic history, there are parts of the universe that know the full story of the universe. The last star is a very long way off. 100 trillion years. You are not running out of time. The sun has 5 billion years of burning left. The universe has 100 trillion years of light to offer. Whatever comes next, whatever minds might exist in that enormous future, and whatever they might discover or build or feel, the darkness is not close. Until the last star dies, there is light, there is warmth. There is the improbable, magnificent fact of existing in the bright chapter rather than any of the dark ones that follow. Look up tonight. The stars are burning. They have been burning for billions of years. They will burn for billions more. And somewhere in the atoms of your body, carried from the cores of stars that lived and died before the solar system formed, is the same physics that will eventually produce the last star, the last black hole, the last positronium, the final photon. You are the universe looking at itself.